Example 15, we wanted to extend the caution when using materialized views and managing the views. So we have a little query down here. We want to find the employees in a specific state. Okay, so what they decided to do is create an inline view to do a complex join. And what they're doing is an outer join using the old Oracle syntax. I actually very much like the ANSI ISO syntax or the OSI syntax, okay, right now as standard syntax. I think it's a little easier and it reduces the chance of an error. If you do an outer join and you decide you extend, if you add any predicates, you have to extend them with a plus sign also. And it was sometimes it wasn't obvious to people. And that also introduces problems when we do. Now we're going to take this view, the employees department view, and we're going to join it in another. It's a complex view to start with an outer join in it. We're going to join it, okay, as an outer join with another table, okay. And the problem with it, because the outer join is hidden within the view, we lose visibility of the complexity of the query if we don't happen to go back and add a look at them. So in this case, we have some suggestions around the views and things to be cautious with. So it's worthwhile having a quick look at the notes at the bottom of the carry. So we just say be careful with the views, especially when you're reusing the views for a different purpose, recycling them. That was the problem I had that we'd had a look at on the demo earlier on in the class, where I built views and then used one out of context. Got so enamored with my wonderful views, I forgot to look at the big picture and realize what was going on. So we have a couple of cautions when using views, when joining complex views. Join to complex views are not recommended, particularly joins from one complex view to another. Often this results in the entire view being instantated. There are two ways it can really run the view. It can treat it as if it was a row source, execute the view first, get a result table, and then apply the predicates to the query on the view to the result, okay? Or it can sometimes push the predicates inside of the view that may open up some access paths for it to use. But by joining complex views, quite often it reduces the ability to merge it together, so it makes it more complex to process. And once we create a result set, there are no indexes on the result set itself. It's an eternal result set, so there are no indexes available on it, so we've got to go and effectively do a full table scan of that result set when we join it with another view. The second caution is watch Trevor getting carried away with views. Don't recycle them in different portions of the application. It's quite often better to write a view that just gets us the data. Views perform well in their own right. I can inadvertently cause extra processing by using the inappropriate views. So that's what the second caution, a little bit of expanded version on that. The third one is use caution when unnesting the subqueries. Subquery unnesting merges the body of the subquery into the body of the statement that it contains, allowing the optimizer to consider them together when evaluating access path and joins. Sometimes that's a good thing, sometimes it isn't. Different circumstances in your data will dictate which ones will make it a good thing. Just be cautious. It's something you want to look carefully at the execution plans. Make sure the way you're doing it is actually giving us the best execution. Also, be cautious when performing outer joins to views. In the case of an outer join to a multi-table view, the query optimizer in 816 and later can drive from the outer join column if an equality predicate. An outer join within a view is problematic because the performance implications of the joins using the outer view are not visible by just using the view. You have to actually explore and be willing to check the definition of the views. So just be careful with those. Next up is the ability to write a combined statement. This is a case where we have a group of SQL statements. We showed two, okay, three in this example, that are passing through the same data. All three of them are queries on the customer table, okay, and we're returning three sets of data from the customer table. That requires the worst case if all of these get done as a full table scan, it will end up you doing 3 full table scans. If the customers is a big table, if I could reduce it to one query and do it as a combined SQL statement, I may potentially be able to reduce the number of passes over the customer table. So the first one is looking for the customers that have a certain gender, male versus female, and a certain country code. Gender generally in a general population is very non-selective. We expect on average 50% will be males and 50% will be females. If we're going to return half the rows, we're not going to use an index, okay? So even if it was possible to use the index, we're returning too many rows to make the optimizer perceive. Plus the other problem is we're doing a count, we'd have to guarantee that the index documents every row if we wanted to use the index on gender. Okay. We may be able to use the index on country code if it's a relatively big table and there's country code is unique, which I would expect it to be generally. Okay, but not on the customers table. If we were looking at the country code table, then it would be unique. We could have lots of customers in the same country. So it's going to be a non-unique index. It depends on how selective it thinks this index is, whether we use it. If it thinks it's inselective like gender, it won't use it, and we're going to do a full table scan. Okay, even though we are looking for a third predicate, customer marital status is not null. Okay, that may open up using an index on marital status. Marital status can have a limited number of values, true or false. Okay. And that means we can't use one index to solve all of this unless it was a composite. And even then, it would probably find it an undesirable index. We'll probably end up doing a full table scan. And the same thing is true, but now we're looking for marital status is not null and single. So if we think people are roughly split 50-50 or 40-60 on single versus married, then we're going to end up with a large number of rows for single, okay, and a large number for married. That's going to be an unusable index. We're going to do a full table scan. So we have a little example of rewriting them. We don't actually run the output, but we do have a little example of showing you how to rewrite it. It wouldn't fit on the slides, so we do it in here, okay, for number 16. Okay, this was our first pass out, and if we look at the output, they didn't include the output for this, but we'll just look at their example, that's fine. If you're curious and you have a practice environment, you could actually rewrite this. So this was the example. We wanted to look at the count of females and of females that have a marital status of not null. We've either had them documented what their marital status, and either is null or single in this case. So we'll end up doing 3 full table scans to solve this. We could rewrite it as one table. Instead of doing the full table scans of 55,500 rows 3 times, we can do it as one. We're doing the count of the original query, the first one, and then we're using a decode to pick up the counts, the sums of the other one. We just want to count, which is a sum of the number of ones that met this condition, the ones that have the marital status of null, and the ones that have the marital status of null and the marital status of single. So it's possible, understanding how the decode statement works and how the sum work, to rewrite 3 queries that may be required for reporting purposes into 1 query. Do 1 full table scan of the data will be cheaper than doing 3. And a lot of times these are used in data warehousing to load certain tables for doing certain specialized processing. So they can actually be useful in that case. There is a second example that we can look at in here, which is doing a little bit further. We are doing the sum of the amount sold in this case, where we're having a look of the products table for product 47 and the sold amount between a certain range of dates. Okay, we're doing, and we want to know who came from channel ID 2. We have different marketing channels to use. Some are direct sales, some are marketing, some are web sales. We keep track of the different way we got the sales. We want to know how the sale came in here. Essentially, we're doing the same major portion of this query again down in this one, where now instead we want the average amount sold. But now instead of through a channel, when the amount sold is less than 29. Okay, is it $29 or 1,000, depending on what their units are. This can actually be rewritten as one statement, once again using a decode statement. Okay, instead of doing multiple passes through the data to solve this, we could solve it with 1 pass through the data. Okay, so now we're doing a sum of decode for channel 2 and the amount sold. Okay, and we being 0, and then the second one to get the other sum, the amount sold minus 29 has to be a non-negative value, and the amounts or the amount sold is 0, and the other. So it takes a little bit of thinking about how to rewrite them, but it is technically possible to rewrite them. And by doing 1 pass, it's cheaper than doing 2 passes. Just 2. This was a little more complex example of using the decode statement. Coming up next is we're going to have a look at example 17, writing a multi-table insert to solve it. In this case, we have a number of inserts we need to do based on a number of conditions. We're inserting into sales a group of columns based on the fact that there's a condition we're looking at from the sales activity table. And then we have, so we're going to insert into the sales record, we're also going to insert into the cost table based on a very similar condition on the sales activity table. And with a little bit of care, this can be rewritten as a multi-table statement. So in our demos, we have some examples. We actually have 4 passes of doing this in our example. So the first one is looking at a simple example. To give an example of how it works, where this is doing some setup for it, we're creating 2 tables, customer single and customer married. Okay, then we're turning on tracing and we're doing inserts to populate the 2 of them. We want to separate our customers into the single customers and the married customers for some reason. Go through. Now, by writing it as an individual insert statements, we're going to have to do 2 passes through the customer table to update the 2 tables. Okay, so we end up, if there are no appropriate indexes, And marital status being single and being married is probably not selective enough to be usable as an index. We'll probably end up doing full table scans. Well, let's have the output just to see if that makes sense or how it actually went to do it. So in this case, we did the pass through the customer to set up the single into our, we're doing an insert as a select. It did a full table scan of the customer table. It cost us, it's an insert, so don't forget it doesn't have the fetch phase. This is the first time we've looked at DML for a while. It only has parse and execute phase. And to update the table, we wanted to select 20,000, just a little over 19,000 rows to put into the customer single table. But we had to look at, since we did a full table scan of customers, we looked at 5201 blocks in memory. Okay, then we have to execute the other query, and we ended up doing a full table scan of the customer's table, and we touched 4059 blocks in memory when we processed it this time. Okay, why is the difference? Because we put 14253 up here, we inserted 19094. So part of the total block processing is reading of the full table scan. It's also inserting the rows into the other table. Those were inserted into other blocks in the other table, and they were accounted for as part of the query. But the net result is we ended up doing 2 full table scans over customer table. Can we reduce that? Well, of course, or we wouldn't have been discussing it, right? So let's look at another way of writing that. Okay, we can use the insert all statement, and then we can put 2 predicates. Okay, one to match where we want to put it into the customer table, and a second predicate, when they're married, we want to put it in the customer. So we're doing one insert, but we're inserting into 2 different tables based on the status of the marital status. If it's single, go into a customer single table. If the marital status is married, then we go into the other table, the customer married table. Okay, and we do it as a select from the customer, so that means we can do it as one full table scan of the customer table. It will reduce the amount of I/O we hope overall. So let's see how this performed. Okay, so we touched 6653 blocks in current mode. We read 3220. These are the inserts. We have to insert, we're effectively inserting all the rows, assuming none of the marital statuses were a null. If they were, it may have missed a few rows. We expect that probably an exception. Or if we had a not null constraint, then it would guarantee all of them had to have rows. And the number of rows we ended up inserting is 33,347. So there are some rows in the customer table that have a null marital status, a fair number of them actually. But we ended up inserting, but we were able to do it as one pass through the customer table, okay, instead of multipass, which is a cheaper operation. If you look at the sum of the time, this was able to do it in a total of 77/100th. The other previous way, it did it in, first one took 54, the second one took 43. So it's almost, what's that add up to, 97? Not quite 100, where it was down to 77. So it reduced the time because we had to do, as a multi-table insert, we really did only one full table scan. We reduced the number of data we have to look at. Some of the inserts were more, but we did it as one statement, and it was the sum of the inserts for the 2 of them. So it makes it a more efficient operation. And we have more to consider. So we have another example in this area. So we'll open that up. Okay, this is a little more complex example. Okay, we're going to insert in the products table based on a select from the products table, and this is really just some setup to make it work. Once we've got the products table with some updated values in it, then we need to go in and process it. So there's a couple of updates we need to do. We need to go in and update the costs for some products that meet a certain condition. The unit code is greater than 80 and it matches this condition. We also need to delete some rows. We decided we don't want the rows for channel 4 that meet these conditions. And then we need to insert some new rows. Okay, they're the ones that we added to insert some new rows into the cost table. So we have to do 3 passes the way it's written here. The question becomes, can we do it as one pass through the data to reduce the cost of doing these 3 statements as a unit? Okay, so the first thing is we look at the cost of doing these real quick just to get an idea of how much it was costing us to do it. For the first one where we were updating, we had to read 1274 blocks. We had to insert, okay, we access them in current mode. Don't forget that generally includes, we were inserting 1669 rows. Why we detach lots of blocks? Well, we got to generate undo before we make the changes. In this case, the undo is fairly simple. And we got to update the undo header because we always have to be able to roll back a transaction if it doesn't commit. And we have to update the fair bit of undo we need to generate. So we touched a lot of blocks in memory to process 1669. And then we need to do that. It has a little more complex. I don't really focus on it. I really want to focus on the cost, this information up here. Then we needed to do the delete, okay? And it had to query 1660 and then had to do some deletes. We have to generate undo to delete 432. But effectively, we had to do a pass through the data. But it was able to find some indexes to help out. Okay, and then finally we do the little piece that does the insert. This turned out to be the cheapest part. We only had to look at 29 blocks. To update 23, we only had 10 rows to insert. But once again, it took some pass through the data to do that. Even though it was a cheaper query, could we reduce the overall cost in terms of CPU and the blocks we process in memory by doing it as a combined statement? So 4 is combining these two. We're just doing the setup because we got rid of it the second one, and then we're doing our combined statement, a merge statement that does all 3 processing as one SQL statement that allows us to go through the base data once. Okay, we're going to have merge into the cost C when this condition is met. Okay, then we're going to make sure it's an equal join for it to meet. The product ID in our cost table matches the product ID in the product table. And then we have our condition that controls what type of operation we do in the merge. Okay, when we get a match on the on condition and the condition above, we're going to update the sales. Okay, we're going to just update the current value of the product, of the information. If we don't have a match and it happens to be channel 4, we're going to delete it. So we're doing the update of the customer table and delete from the customer table, okay, with this branch. And then we have another branch when not matched, then we don't find a match on any of these conditions. Then we're going to insert the new row. So we can do one pass through the data, okay, by joining them together and do all three steps as one pass. And of course, the proof of the pudding is see if it overall reduced it. So in this case, we needed to look at 966 and 632 in current mode to process 1679 rows. And the time was just over 7100s, and we did it as one SQL statement. Comparing that with the overall blocks we had to process in query mode, we did 1274 for this one, 668, so we add them together, you're looking at about 2,000. And then we added a little bit, 230, okay. For this one, we did an overall in query mode 996, so we reduced it in half by doing one pass. Yay team, we won! Very nice. We can also check the current to see if the reduction, this took 1633 in our final form. In our earlier version, we'd have to add them up. This was the starting at the top. So 3,500 added to 1392, we'll call it 1435.49, almost 5,000, way above it now, and a little bit extra, it's not going to make a big difference. So about 49,000 versus 62.32. So once again, pretty well a wash. It was pretty close on this leg. Okay. Next thing is to check the timing. A little less than 70 seconds, 69/100ths of a second to process. What was the total times of these? The last one wasn't very much. It was 0. This was 15. This was 45. Add them together. Okay, you're looking at a CPU time of actually a little bit more. Once again, go with the logical blocks, okay? Because if you scale up to larger volumes of data, you may see a larger payback. In this one, it was actually a little bit more expensive to do it in CPU processing as a single statement. So your mileage may vary. Test, test, test. It just opens up the opportunity of doing them a different way.